Hi, welcome to 8.6, our last section in Chapter 8. We're going to be talking about the dot product and its uses. Dot product's really cool. In mathematics, the dot product, also known as the scalar product, is an operation which takes two vectors over the real numbers and returns a real valued scalar. So what's kind of cool about this, we go from having vectors to a scalar in the end. It is a standard inner product of the Euclidean space, and that is, this whole definition came from Wikipedia. Not a fan of Wikipedia, but there really wasn't a good definition I could find anywhere else for the dot product, what it is. But let's go ahead and talk about how to do the dot product. Really a neat thing to do. Given two vectors, u being u1, u2, and v being v1, v2, the dot product of u dot v of the two vectors is the scalar defined by u dot v is u1, v1 plus u2, v2. This gives you just a single number in the end, not a vector. Let's do some calculations here. I'm going to move this up so I can do maybe both examples in one. Okay, so we're going to calculate the following products. 2, 4 times negative 1, 1. That's going to be 2 times negative 1 plus 4 times negative 1. Negative 2 plus negative 4 is negative 6. 1, 2.34, it's going to be 1.3, 1 times 3, plus 2 times 4. 3 plus 8 is 11. Okay, now we're going to go a little further. We're going to find the indicated quantity. Now when we do u dot v, that's going to give us a scalar. We have a scalar times 2, then that scalar is being multiplied by this vector v. So our u is negative 2, 3, and v is 4, 4. So look at u dot v first. That's going to be negative 2 times 4 plus 3 times 4. That's negative 8 plus 12, which is 4. So when we do u dot v times 2v, that's 4 times 2 times the vector v, which is 4, 4. And that's going to be 8 times the vector 4, 4, which is going to be 32, comma 32. 8 times 4 is 32. Okay. Feel free to pause as usual. Moving on up. Elementary properties of the dot product. Given two vectors, u is u1, u2, and v is v1, v2, and a scalar a, the following hold. U dot v is v dot u, 0 times u is 0, u dot v plus w, now again these are all vectors, is u dot v plus u dot w. A scalar times u dot v is a times u dot v, or u times a dot v, u dot a times v, excuse me. And here's a cool one, u dot u is the magnitude of u squared. So this next example, we're going to use that last property, number 5. Find the magnitude of u using a dot product. So the magnitude of u is going to be u dot u, which is 10.3.10.3. That's 10 times 10 plus 3 times 3, 100 plus 9, or 109. And so that's the magnitude squared. Put that squared here. So the magnitude of u would be the square root of 109. There we go. Now the dot product theorem, really cool, useful theorem. Let two non-zero vectors u and v be depicted so that their initial points coincide. And let theta be smaller, the smaller of the two angles formed by u and v, so that theta is between 0 and pi. Then u dot v is equal to the magnitude of u times the magnitude of v times cosine theta. Let me just point out, from 0 to pi, that's what arc cosine or cosine inverse produces. So not a coincidence there. We want to find the angle between the given vectors. So notice we're given the vectors, and from this we can find u dot v. We can find the magnitude of u, and we can find the magnitude of v, and then use that to find the angle between them. So u dot v is going to be 5 times 3 plus 4 times 2. That's 15 plus 8, or 23. The magnitude of u is the square root of 5 squared plus 4 squared, the square root of 25 plus 16, which is the square root of 41. The magnitude of v is the square root of 3 squared plus 2 squared. That's 9 plus 4, square root of 9 plus 4 is square root of 13. So what we want to find is this cosine theta, or actually just want to find theta. So we did u dot v equals the magnitude of u times the magnitude of v cosine theta. What we have is 23 equals the square root of 41 times the square root of 13 times cosine theta. So 23 over, we divide by this, square root of 41 times the square root of 13 equals cosine theta. So cosine inverse of 23 over the square root of 41 times the square root of 13, that's going to be our theta. Theta is going to be arc cosine of this quantity. So theta will be 0.0867 radians, and if you convert to degrees, theta will be 4.9697 degrees. Let's go ahead and look at example 5 then. We're going to use vectors to find the interior angles of the triangle given the following sets of vertices. So the nice thing here is it's a triangle, so we have to just find 2, and then we can use the property that the sum of the angles of a right triangle, or of a triangle, is 180 degrees. There, a little more space. So we have a point at 0, 0. At 0, 5, and at 3, 6. Okay. So let's look at some vectors here. From 0, 0 to 0, 5, we'll call that u. So that u would be equal to 0, 5. No horizontal change, 5 is a vertical change. V, we'll define that to be up here. So horizontally it's going over 3, vertically it's going up 1. And then W will be this last one here. Starts at 0, 0, goes to 3, 6, so horizontally 3, vertically 6. So let's get the angle between u and v. First, the magnitude of u is going to be the square root of 0 squared plus 5 squared, square root of 25, which is 5. The magnitude of v is going to be the square root of 1 squared plus 3 squared, I should say 3 squared plus 1 squared. Same answer though. That's 9 plus 1, which is the square root of 10. Now u dot v is going to be 0 times 3 plus 1 times 5. And that's going to be 5. So we're going to have u dot v equals the magnitude of u times the magnitude of v cosine theta. So u dot v over the magnitude of u times the magnitude of v equals cosine theta. So theta will be equal to arc cosine of u dot v over the magnitude of u times the magnitude of v. So theta is going to be equal to arc cosine of 5 over 5 times the square root of 10. And that comes out to be, in degree mode. Okay, so we're doing we'll call this theta bar because this is a reference angle. Theta bar is cosine inverse of u dot v over the magnitude of u times the magnitude of v. So theta bar is cosine inverse of 5 over 5 root 10. And this comes out to be 71.565. Now, I say that's reference because if you look over here, this is an obtuse angle. And that's an acute angle. So what it means then is theta is going to be 180 degrees minus the 71.565 degrees. So theta would be 108 point, let's go to 43 degrees. And that's going to be this angle up here. Now let's get one more angle. How about the angle between V and W? We'll call that alpha. So for that, V and W, we need the magnitude of V, magnitude of W, excuse me. That's going to be the square root of 3 squared plus 6 squared, 9 plus 36, square root of 45. So we need also V dot W. That's going to be 3 times 3, so 3 times 3 plus 1 times 6. That's 9 plus 6 is 15. If we follow the same setup, our alpha, and that's okay, we don't have to do alpha bar because this is going to be acute. Alpha is going to be cosine inverse of our V dot W over the magnitude of V times the magnitude of W. So alpha will equal cosine inverse of 15 over the square root of 10 times the square root of 45. And that's going to be 45 degrees. Okay, so finally, we need one more angle. Let's call this phi. Phi will be more vertical than that. It's going to be the 180 degrees minus the sum 45 degrees plus 108.43 degrees. So phi is going to be 26.57 degrees. So our angles are, theta is 108.43 degrees, alpha is going to be 45 degrees, and phi is going to be 26, keep drawing that wrong, 26.57 degrees. Okay, and that's it for that problem. So we'll move on to example 6. Find u dot v where theta is the angle between u and v. Okay, so just recall, u dot v is the magnitude of u times the magnitude of v times cosine theta. So u dot v is what we're trying to find. It's going to be 4 times 64 times cosine of pi over 6. So u dot v is going to be, that's 256 times the square root of 3 over 2. U dot v is going to be 128 times the square root of 3, which is 255.98. That one's a lot easier than the last one. Orthogonal. Orthogonal means perpendicular, so two non-zero vectors, u and v, are said to be orthogonal or perpendicular if u dot v is 0. Why would it be 0? Well, if they're orthogonal, that means it's a 90-degree angle, and cosine of 90 degrees is 0. So this is equivalent to saying that the angle theta defined by the two vectors is a right angle. So for example 7, we're told to find two vectors orthogonal to the given vector. So let's say it's going to be u dot 4, 1 must be 0. So u would be made up of u1 and u2. So 4 times u1 plus 1 times u2 equals 0. So 4 times u1 equals u2, negative u2. So you have choices. You can be creative. You can think, okay, what if u1 equals 1? Well, then u2 must be negative 4. So one vector would be 1 comma negative 4. If u1 equals negative 1, then u2 equals positive 4. Negative 1, positive 4. Here are two vectors that are going to be orthogonal to our given vector. Those aren't the only choices. You could say like u equals 2, u equals 5. That's what I went with. Okay, are u and v orthogonal, parallel, or neither? So first let's look for orthogonal. U dot v is going to be negative 12 times 1/2 plus 30 times negative 5/4. That's going to be negative 6 plus, this reduces, but look, they're both going to be negative. Let's see, this reduces there, leaves a 2 and a 15, so negative 75 over 2. Excuse me, that's not equal to 0, so they're not orthogonal. Excuse me, sorry about that. Are they going to be parallel? Is the next question. Now, parallel vectors are multiples of each other. So can I multiply negative 12 by something and get 1/2? Let's see, negative 12 times x equals 1/2. So x would be negative 1 over 24. So if I multiply a 30 by that, 30 times negative 1 over 24, that's going to be negative 30 over 24. We can reduce that. If we divide out by 6 on top and bottom, we get negative 5 over 4. Hey, that worked out. So that means u is a multiple of v, or v is a multiple of u. Therefore, u and v are parallel. Okay, let's go on to page 4 here. Projection of u onto v. You got to read this the right way. It's really critical in doing these problems. Where does the u go? Where does the v go? Projection of u onto v. Let u and v be non-zero vectors. The projection of u onto v, so the v is the subscript down here, is u dot v over v squared, the magnitude of v squared, times v. So this tells you how much of the vector of u is on v, as in component form. So we want to find the projection of u onto v. So first let's find u dot v. That's going to be 2 times 1 plus 2 times negative 7. That's negative 7 as a result. No, that's not right. Second. What's 7 times 1? Okay. That's going to be 2 plus negative 14, so it's negative 12. There we go. Then we want to look at the magnitude of u. Actually, we don't need the magnitude of u here. I think we just need the magnitude of v. The magnitude of v is going to be the square root of 1 squared plus negative 7 squared. That's 1 plus 49, which is the square root of 50. So our projection of u onto v is going to be negative 12 over the square root of 50 squared times our 1 negative 7. So that's going to be negative 12 over 50 times 1 negative 7. That's going to be negative 6 over 25 times 1 negative 7. So as a result, it's going to be negative 6 over 25, comma, 42 over 25. So that's our projection of u onto v. To get the other part of this vector, so we have the part that's on v and the part that's perpendicular to it. We do u minus the projection of u onto v. So that's going to be 2, 2 minus our negative 6 25ths, comma 42 25ths. And we get from that 56 25ths, comma 8 25ths. So u can be described as the part that's on v, which is our negative 6 25ths, 42 25ths, plus our 56 25ths, 8 25ths. So this part is our projection of u onto v, and this is the perpendicular to the projection of u onto v, the part that's perpendicular to it. The part that's on v and the part perpendicular, that all makes the u up. Okay? Let's go on to the next one. I can relate to the next one because I am a Cub Scout leader, and we have Cubmobile races where the kids sit in these cars they build and they race down the hill. Thing is, this one has a child sits in his go-kart, and ours are non-powered. I'm assuming this is non-powered. Sits in his go-kart at the start of the position of a race at the top of a hill. If the hill is a slope of 3 degrees, we do more than that. We do more like have a ramp, and it's more like a 40-degree angle. Then the hill maybe have a 30-degree slope. And the child and go-kart have a total weight of 250 pounds. What force is required to keep them stationary at the start position? So we have here There's our kid. So I did that. Okay. Kid there with the windshield going on. 3 degrees, so we have 3, not 30. Now, if we think about this, this is 3 degrees. Think of a 3-degree drop for the hill. This is B and this is 1. Tangent of 3 degrees is going to be opposite over adjacent, B over 1. So that B equals 0.0524. I write that because this gives us a relationship between these two, the horizontal and the vertical. So in our system here, I'm exaggerating the 3 degrees on purpose. If this is our actual vector v, here's our u, this is 250 pounds going down to the earth. What we want to know is the projection of u onto v. That's going to be u dot v over the magnitude of v squared times v. So what's our v? Our v vector, that's why I broke down here, v is going to be 1, 0.0524. What's our u? U is going to be 0, negative 250. So we want to look at a couple things. What's our u dot v going to be? Our u dot v comes out to be 0 times 1 plus negative 250 times 0.0524. I wrote these backwards, but it's fine. I wrote a v dot u. It's the same thing, though. And we end up with, oh, this should be negative there. That's negative. 13.10. The magnitude of v is going to be the square root of 1 squared plus negative 0.0524 squared. And this comes out to be square root of 1.0027. Okay? So I think we have all the pieces here. Our projection of u onto v is going to be our u dot v, which is 13.10 over the magnitude of v squared, so that's going to be 1.0027 times our v vector, which is 1, negative 0.0524. So this comes out to be 13.06 times 1, negative 0.0524, which is 13.06, negative 0.684344. So that's v in component form. So the magnitude of our projection of u onto v is going to be the square root of 13.06 squared plus negative 0.684344 squared. So that's 13.077 pounds. Okay. That's the force you need to keep it, to hold it back from sliding down the hill. Okay, let's go on to the last one then. Feel free to pause on that. Moving on here. The last concept is work. Work equals force times distance. So if d represents the vector of motion, making the magnitude of d the distance traveled, and F is the force applied, not necessarily in the same direction as d, then the component of force in the direction of motion is magnitude of force times cosine theta, where theta is the angle between the two vectors. So the work done then is the product of the magnitude of D and the magnitude of force times cosine theta, or work equals the magnitude of D times the magnitude of force times cosine theta. In dot product form, work is D dot F. Okay, so a child pulls a sled over the snow, exerting a force of 25 pounds. Here's my sled. So 25 pounds is being pulled on this rope. Now it says the rope is 35 degrees to the horizontal. So this is 35 degrees. If the child pulls the sled a distance of 80 feet, what work has been done? Well, the magnitude of the distance is 80 feet. The magnitude of the force is 25 pounds. And our angle is 35 degrees. So the work is going to be the magnitude of distance times the magnitude of the force times cosine of 35 degrees. So work is going to be 80 times 25 times cosine 35 degrees. And that's going to be 1,638.30 foot-pounds of work being done. And that's the end of this section. Okay. Let me know if you have questions. Talk to you guys later.